I'm Sean Rager, and this is my Lab 4 for Georgia Tech Physics 2, Circuits and Capacitors. The purpose of this lab was to investigate the relationship between resistors, batteries, and capacitors using measurements of current and voltage. This lab was done in CCK software, so their in-software tools for measurement were used. And later on in the lab, we measured a value for the time constant of a circuit, showing the time dependence of voltage in an RC circuit. Here are the physics principles we used, most notably Ohm's law, which shows that the current in a section of a circuit equals the voltage drop divided by the resistance of that section. We also have rules for series, parallel, and capacitors. And next we see Kirchhoff's laws, first of them being the node rule, which shows that the current flowing into a node equals the sum of the currents flowing out, and the loop rule, which shows that in any cohesive loop of circuit, the summation of voltage changes equals 0. Now our procedure consists of two scenarios, the first being a series circuit. First we calculated the equivalent resistance for the circuit, and then we plugged this into the Ohm's law equation to find that our current was expected to be 0.02 amps, which was exactly what it was in the experimental data. And when the circuit was built backwards for the ammeter, we saw no change in the current. In this scenario, the ammeter was replaced with a voltmeter, and current was not flowing, so the ammeter read nothing. But we still saw the voltage drop of -3 volts, as the batteries are still part of the circuit. So when it is closed by the voltmeter, we have to see that voltage drop somewhere, as there is no current flowing through the resistor, so they have no voltage drops in and of themselves. Here we see the circuit is closed back together, and we measure the voltage drops across each consistent section of circuit, and we saw three notable changes. The first in AB being a voltage jump of 3 volts, CD a voltage drop of -0.96 volts, and EF a voltage drop of 2.04 volts. When we graphed this, we saw that the loop rule held true. We started and ended at 0 volts, showing that the net summation of voltage changes equals 0. Here we saw a few edits to our system. First, when the voltmeter spanned the ammeter, it did not change the resistance or the current in the circuit, as the resistance is very high in the voltmeter, so it did not provide another path for current to travel down, so the current did not change. But when the ammeter was placed in parallel alongside a resistor, there was a new path of least resistance, and the current of the circuit changed, and it actually increased thanks to this new path. And through our hand calculations of resistance, we saw that the resistance of the 47 and 100 ohm resistors were about what we expected, and the wire and ammeter resistance were 0, as this is an ideal scenario, so they are modeled as 0 resistance portions of the circuit. Now looking at our RC circuit, first we attached the battery, capacitor, and light bulb all in the circuit, and the capacitor started off by charging. Current flew rapidly at the start, and the light bulb was bright because of this, but as charges built up on the capacitor, current slowed down, and the light bulb grew dimmer. In the next phase, we took the battery out and reconnected the circuit and allowed charges from the capacitors to flow through the circuit. And again, the light bulb was glowing bright at the start as current was high, but as charges dissipated from the capacitor, current began to decrease more and more slowly over time, but it did decrease, and the bulb grew dimmer. And we can see this exponential decay of both current and brightness in our graph, where we graphed potential difference and time. We also saw that as the resistance of the light bulb increased, the time to charge and discharge increased as well. And here we see our calculations for the time dependence of voltage in this RC circuit. Our data is on the left, and this was graphed. We graphed the natural log of the change of voltage over the initial voltage drop. We graphed that alongside time, as our equation showed that the slope of this line would equal -1 over the time constant of this RC circuit. And when we plugged in our values, we got that RC is approximately equal to 6, which falls in line with our initial hand calculations, as we used a resistance of 20 ohms and a capacitance of 2 farads. Our hand calculations shows that our RC should be 6, so this is in line with our experimental data. To conclude, if we had done this in real life, our ammeter would not have been perfectly ideal, so it would have had some resistance, and this would have decreased the current flowing through our circuit. Additionally, in a completely ideal model in which there is no resistance in batteries or wires, the equivalent resistance of the system would have been 0. This would allow for a limitless current that would charge the capacitor instantly. As we saw in our experiment, this does not happen. It does take some time to charge the capacitor, and this time would not be instantaneous, but with the minimal resistance of wires and batteries, it would charge and discharge quickly. This concludes my lab for Georgia Tech Physics 2. Thank you for watching.